The New Quantum Era,
a podcast
by Sebastian Hassinger
and Kevin Roney. Welcome back to the New Quantum Era. Today we've got a really interesting interview with James Whitfield, who's a professor over at Dartmouth.
Yeah, Kevin, James and I actually worked together at Amazon Web Services in the quantum team, and I thought it'd be really great to have him on the podcast. I find all of my interactions with James delightful and also really, really interesting and informative. He has more of a quantum chemistry background, and he brings that sort of sensibility to his work in quantum information science.
Great find, Sebastian. So I guess just for a prequel for our audience, in this interview, we'll be covering really three main topics. One is, I thought it was really good, fresh, new detail on the specific areas, right, of chemistry, of quantum chemistry, where you might be able to sort of foresee adequate progress in quantum computation and its merit towards cracking key problems in that domain. So fascinating detail, I thought. Second topic that James got into in some degree, some detail, was an extended dialogue on the intuitive nature, right, of how to perceive entanglement within quantum states and how those manifest in quantum algorithms. So really good material for people that are trying to get on top of that challenging concept. And then the third area, really exciting for me, was to hear James's perspectives on how to better enhance pedagogy in quantum computers and in quantum computation and information science, both in the K through 12 range and at the grad level. So, three rich and fun topics. Good material today.
Yeah, excellent. All right, here we go. Hey, everybody. Joined here today on the podcast by James Whitfield, a colleague of mine, actually, Amazon visiting academic, as well as associate professor of physics at Dartmouth University. Thanks so much for being with us, James.
Yeah, I'm happy to be here. Yeah, from Dartmouth College.
Sorry.
No big deal. It's tough. It's tough. There's like a really interesting history about why it's college, not university. There was also Dartmouth University that was parallel with Dartmouth College and went up to Supreme Court.
Are there two different institutions?
No, one got shut down.
Oh.
One got shut down. It was like a whole Supreme Court case. So Dartmouth University.
You want me to do it over?
No.
I can do it.
It's a nice piece of a nice fun fact about Dartmouth. Right?
All right.
I think leave it in, right?
Cool.
Anyways,
podcast verite.
Yeah, that's why anyone cares at Dartmouth. I think it should be a university because they have everything for a university. But
right, yeah. It's very well rounded. The offerings academically. There's solid science and humanities offerings.
Yeah,
right?
We had one of the earliest courses in quantum information science. So,
cool.
Lorenzo Viola has been teaching this for a long time.
Wow. Is that where you got into QIS, or had you already?
I've been in quantum information science for a long time. So I guess a little bit about me. I did my undergraduate at Morehouse College, and before that, I just really liked doing math. It was a nice way to kind of calm down. And so I would, be frustrated with whatever, and you sit there and do some integrals, right?
I'm with you. That's great. That's great therapy. Yeah, it's as good as meditation. Yeah, no doubt, man.
Exactly. It's like
I don't know. I bake bread. To each their own.
See, that's chemistry, right? So now we switch sides already.
Yeah.
Right? So I did math like that, and then I ended up started off. I was in pre-med, and then I didn't want to be a doctor at some point, but I had a bunch of classes in chemistry. And then I had a bunch of classes in math. Then I graduated. What I do next? And I went into quantum chemistry, where it's really nice intersection of the two. I think my senior year, one of my professors, Troy Story, taught this class on on physical chemistry. And this is borderline, if you change the words around, you say physical chemistry, chemical physics, physics of chemistry,
right,
chemistry
right,
of
right.
physics. And it's a whole bunch of like, they mean nothing differently. And so I took this course and it was so much linear algebra in it. So from quantum chemistry, so from doing math in chemistry as a major to just doing more math in chemistry to doing more math of physics of chemistry, then you're just doing physics. And that's how I ended up in the physics department. Just, step by step by step,
Very
moving
cool.
more over to physics. Physics has had a much better reception for quantum information science. Chemistry is starting to adopt it more now, but when I went up for job searches, I was I searched in both departments, and I ended up finding a position in with what I was doing. I've been doing quantum chemistry and quantum computing, and all associated different types of projects, from quantum walks to thinking about measurements, all sorts of things inside of the realm of quantum computing and quantum chemistry. And so, doing some quantum chemistry projects around basis set designs. I have some fantastic graduate students thinking about this. So we've been playing around with the mathematics, thinking about how the tooling goes, thinking about what is second quantization, how do we transform things from being descriptions of quantum chemistry to descriptions that are of qubits. How do we take that, start thinking about how that applies more broadly to locality of systems? How does that apply to tensor networks? How does it apply to different aspects of mathematical physics, mathematical chemistry, chemical mathematics? And it's just a nice, fun play area.
What's the simplest way to explain what quantum chemistry is, as opposed to, because you're not talking about quantum computation applied to chemistry. Quantum chemistry is sort of a subset of chemistry itself, right?
Yeah, that's a great question. So I would say the way someone explained it to me a long time ago at my first internship, he said that the goal of computational chemistry is to put all the wet chemists out of business. We should just be able to, type in the algorithm and get back an answer. And with machine learning, this is becoming more and more of a reality. But nonetheless, the point being is that was the goal of computational chemistry. You do not have to mix the chemicals to find out what happens inside of a reaction, to figure out what geometry it is. You don't need to shine a laser. You don't have to do spectroscopy. You don't have to apply your NMR device at all. You have some computational way of justifying what you've seen physically, or guessing what you should see physically when you go to experiment. And so it's a way of complementing experiments with theory. That's where computational quantum chemistry comes in.
And that very remark, I mean, that's a great, I think, lead into this sort of interesting area that motivated us to invite you onto the podcast. And again, really thank you for making the time. But there's so many people in the quantum computing ecosystem that point at molecular geometry, physical chemistry, all that stuff as one of the lead possible outcomes, right, of quantum computing showing huge breakthrough new results. And it just appears to me that there's actually a lot of I don't know, maybe not well understood, poorly understood facets of those problems in quantum computing. So we were hoping to dive into that into some detail. Do you have any framing remarks on the merit of quantum computing in its early phases in terms of its applicability to physical chemistry?
Yeah, I mean, I have a few. I think one of the most interesting things, I think, both definitely inside the news media. Okay, it's not even trying to reach these guys because it's a bit hard to really explain all the details. But even in the scientific community, there's quite often a missing piece that a lot of people skip over when they're thinking about what to do with the quantum device. These variational quantum eigensolvers, I think this is what you mentioned, geometry optimization, all these optimization problems, all are heuristics. There's no guarantee you will get a speed up. There's some controversy on the archive now about Grover search has no speed up. I haven't read the article. I won't comment any more than to say I don't think I buy it wholesale. Okay, I don't know what it says, but I just the point being is that on these problems that are NP hard, the most you could do is Grover speed up. And so that's the best you can do. Okay, there's some questions of implementation, which is what I think a paper gets at. But optimization is not where quantum computing is expected to make huge breakthroughs. And so what I think the main missing disconnect inside the community about how computational chemistry can be used with respect to quantum computational science, so computer science, thinking about what can be done. For computer science, optimization of quantum wave functions is extremely hard. This is the Quantum Merlin author class. However, this means that you shouldn't expect quantum computers to do any better I mean, maybe better, maybe not, depending on heuristic, but there's no promise there. And so all these optimization problems don't have any promise other than rather than square root speed up on something like using Grover search.
Per Grover, yes. Makes perfect sense. This is an excellent kickoff. And again, really a fascinating topic for me. Yeah.
Yeah. On the flip side, there is this notion of time evolution. So when you do time evolution, this is very different than thinking about optimizing. And so this is where I think a lot of distinctions lost, even inside the elite community of people who really are building quantum algorithms. They're not always thinking about how dynamics can be used and how that can be utilized to do something. And so thinking about problems that are dynamical in nature rather than optimization in nature are really two different complexity classes from a computational computer science point of view.
Mm-hmm. That's really a very, I think, apt remark. And our audience has got a diverse array of different levels of depth of mathematics. Could you maybe just, for some of the people that are more on the tech end and not math hobbyists, underline and more deeply elucidate that distinction?
Yeah, of course. So if you think of optimization, you want to find the best way of doing something. And this is saying that you have many different settings. You have to go through all the different settings to find what is the best, what is the optimal for whatever you're trying to optimize. Could be anything. This is a very generic set of problems. But these problems are generically hard. Generically, just there's a complexity class of difficult problems, and you can classify all problems that are extremely difficult to a certain set of problems that you can answer quickly, that you can check the answer quickly. And this is true whether in the quantum or in the classical setting, but this is just for problems we have to try every instance. If you get the right instance, you can check it easily, but getting the instance, you have to go over all settings. Okay, this is one class of problems called optimization, and this is a very broad class. On the flip side, when I say time evolution, what I mean is that you're given some initial state, and you just want to propagate it forward in time. So you can think one of the really fantastic stories is thinking about modeling the solar system. You have some, where the planets are, you have some initial set of conditions, and then you think about where it will be a month from now. You have some data, and you see how it goes forward in time. Depending on the exact problem, you can propagate forward in time efficiently or not. For the solar system, if you don't include the interaction between the planets, you can do forward in time as far as you want. However, if you include the interaction between the planets, it becomes chaotic, and you can only propagate so far into the future.
Huh.
So,
and is the analogy there that you can model the relationships through entanglement in a gate-based quantum computer?
So that's close. I think I would phrase it slightly differently. If we think about what happens inside of quantum time evolution, is that your entanglement is growing linearly in time. This is whether you use gate-based or any other sort of situation where you're doing some sort of entangling gate. If that's part of your evolution, which generically speaking, it's part of your evolution operators, you have to do something very clever to make it not universal. And so if you have a universal set of gates, when you propagate in time, then you just expand out and you'll see what happens later in time. However, the entanglement of that system grows with the length of time you're going, such that classical simulations, for example, tensor networks, will fail just because the entanglement's growing in time. The number of variables you have to keep track of is growing in time. This makes it very difficult.
The computational resources required are growing exponentially.
Exactly. Well, yeah, for the algorithms we have.
For the classical algorithm.
Exactly.
Interesting. And so, look, I just as a hobbyist of studying this, I'm no accomplished scholar, but I mean, just as a hobbyist, it's clear. I mean, there's been almost 100-year quest, right, in terms of applying, the axioms of quantum mechanics to the area of chemistry to find decent algorithms. It's a very well-developed field with still lots of unsolved problems, but still lots of progress. And so, I mean, again, it feels like many people in the QC community point at this area as something which feels like, quickly within grasp, one of the very first QC problems that will be cracked, molecular geometry. But you seem to be showing at least some doubt about that. Is that do I read you correctly?
I think I'm kind of not getting across exactly what I want to say. So it's not so much that I think quantum computing for geometry optimization. Geometry optimization is only one problem that people discuss. There's many problems that are discussed.
Yes.
And most of the literature is around electronic structure, where you're optimizing the electronic wave function. This is where you're not doing geometry optimization. Geometry optimization is more thinking about the nuclei are. Of course, people do this as well. But normally when you do geometry optimization, you can apply classical mechanics. And this is where you get these really nice molecular mechanics experiments, molecular dynamics. These are almost all classically done. Electronic structures dictate what are the binding energies, what are the rotational constants, what are the things that are holding things together. Then you model as springs later. But to actually get what the strength of that spring should be, you need to know what the electrons are doing. And that's where electronic structure comes in. And this is where a lot of the effort inside of quantum computing has gone in. This is where my work has been for almost since 2006. I've been thinking about electronic structure on quantum computers. But these electrons are dictating where the nuclei are, what the forces nuclei are feeling, which way they're going to move next, what the forces on them are, what the rotational moment, moment of inertia, all these sort of quantities are coming from electronic structure. And so this is why this is a huge important aspect of thinking about how do we get to molecular dynamics. You have these very well characterized potential energy surfaces from the electrons moving around. Then that dictates where the nuclei will move.
So, and you seem to be touching on what's called commonly the Born-Oppenheimer optimization. Yes, that you could perhaps start with a good guesstimate of the
approximation.
Position of. Did I not say that? Please forgive me if I said that wrong. Yeah, the Born-Oppenheimer approximation, right? Not optimization. Yes, and it places the nuclei, and then the larger problem is, well, what's the configuration of the electrons, which is a much harder problem. Do I have that right?
I would say an easier way to say that is that it's also called the clamped nuclei approximation.
Much better, much easier to say.
Yeah, and also I think more visual because you can see the nuclei clamped into one spot. And then you think about how the electrons are moving around them, and you clamp them in a different spot and see how the electrons are moving around them. And so you clamp the nuclei, and then you let the electrons move.
And so for that latter problem, the much more difficult one of the shape of the electrons as they cluster around these nuclei, that comes from a solution can be found if you've got deep insight on Schrodinger's equation for the quantum correlations between these electrons. But that's a hard problem to solve analytically. It's really impossible analytically and very difficult, very challenging numerically. Yes.
So there's two ways to think of the Schrodinger's equation. If you go back to wherever, you may or may not have heard of it, but in Schrodinger's equation, you can think of it as a linear equation telling you about eigenvalues and eigenvectors, or you can think of it as a differential equation telling you about time evolution. And these are not at all the same approach to thinking about the problem. When you think about finding the lowest energy state, you're solving the eigenvalue problem. In the other case, I'm talking about dynamics. You're using the Schrodinger equation as a way to propagate in time, the differential equation version. If you do the differential equation version, this is what quantum computers are promised to do under the complexity class BQP. This is just doing time evolution of the quantum device. That is following Schrodinger equation as a differential equation, and that's what quantum computers can do well. And that is thinking about spectroscopy, about excited states, about what happened when you hit it with a photon, how the system evolved from there. These are problems in quantum chemistry that people have not been approaching for hundreds of years, or for 100 years rather, because what they've been doing is ground states. There's a ton of heuristics for solving for ground states, for figuring out what geometry it is, what is the configuration of that state, what is the spin of that state, all sorts of properties of the ground state. And at equilibrium, we have fantastic tools for understanding molecules at equilibrium states and their electronic structure. But we start talking about the excited states, what is the ordering of the spin states, sort of questions of that nature become much more difficult. And these are questions that you can answer with the quantum computer by doing dynamics.
Got it.
And this is where you start to see dynamics coming in. When you think about this, just to kind of maybe wrap a little bow around it that might help out you guys or your listeners, is that when you think about dynamics and you think about what is spectroscopy in a quantum chemistry context, you're doing a Fourier transform of something. You've done the time evolution and you Fourier transform that time evolution. And if you think about the heart of Shor's factoring algorithm, that's also a quantum Fourier transform. So you can see the time evolution is the same game. You're doing a time evolution, you're doing a Fourier transform over it, and that's telling you about the spectra of something. That's interesting. But that's a dynamical quantity you're getting out that's not about optimizing initial state. Take initial state, characterizing it in time. What happened?
Interesting. And in terms of applications, James, like what types of things would you be able to do if you could model those time evolutions, those dynamics?
That's really interesting. It's really interesting. I would say that as quantum chemists, it's not been looked at as much. And I think in many ways, the fact that there's not as many ready to go applications for what you can do if you have time dependent quantum control um, is because when you have a hammer, everything looks like a nail.
Yes,
Yeah.
right.
There's a lot of experience in solving ground state problems, from DFT and different techniques of DFT and how to optimize the code, how to use, GPUs, how to, use screensavers, on and on and on. And all these different methods classically that have branched out all around finding this ground state and better heuristics for it. So the heuristics for ground state are actually really good, which makes it seem like not a great place to try and get a quantum computer to do something because the heuristics are really good already. Why should we expect that we'll be able to get a better heuristic on variational problems? We already have great heuristic classically. And we're looking in very niche, very dark corners to try and find, a gem when there's a whole big array of light that no one really knows how to tackle.
Right.
And so it's not.
Well, and we can marshal like millions of CPUs and have incredible accuracy and resiliency and fidelity in our computations classically. And on the quantum side, it's kind of it's in a very nascent state, let's say.
Yeah, that's true.
So yeah, it does seem like the wrong place to start looking. So what you're saying is that essentially it's familiarity that's driving the early explorations in using quantum computers for quantum chemistry, and your gut feeling is that it's it's in the areas we haven't tried doing with computers yet because they're just too hard classically that might yield the first results. That's interesting.
I had a few colleagues when I was in grad school. They gave talks about doing chemical reaction dynamics, and they just doing H2 plus H is like, that's like where they're at, and it's huge, expensive problems, and they have to do the surface. So, where they're at now, to say it's not many quantum chemists working on, it's not a huge community. I mean, there are some codes that do time-dependent TDDFT, things like this that are there. So it's not saying it doesn't exist at all. So I don't want to, putting my colleagues out out. But there's a lot more space for more to be done, and it's not as commonplace, doesn't work as well. Ground state DFT works fantastic. TDDFT, they're thinking about ways to make better approximations. So it's not as well trodden. This is a lot of things around what excited states, what happens when you hit something with the laser. If you think about some applications of the boson sampling problem, this was to molecular spectroscopy, rotovibrational spectra. So this also is another place that you can see spectroscopy coming into the forefront of what's happening, thinking about time-dependent quantum mechanics.
So it's really a very fascinating conversation for us because for a long time in many of these interviews and conversations, again, there's this nuance of the difference of the types of domains where you could expect to see progress. It's really not been underlined. So this clear separation between these subdomains.
People just say chemistry.
But also it's really so illuminating to hear you sort of so directly point at how there's this long history of this focus on the ground state optimization problem, not solved, but boy, there's been a lot of progress, and with the rise of ML, even more. But these other dynamics areas, I mean, who knows? There could be a gigantic new outbreak of like huge breakthroughs, right, in chemistry from this very domain. It's almost unstudied at this point because it's so hard.
Exactly. I mean, that's a good way to summarize.
And James, does it require, like you were talking about like VQE as an approach, and that's in large part sort of trying to figure out useful things we can do with NISQ machines. Do you think that what you're describing in terms of time evolutions, you need fairly large numbers of fault-tolerant qubits to do useful calculations, or is that something that NISQ or even analog devices like QuEra might be able to be helpful with?
I think there's some pretty easy things that will convince me. I mean, this is, Simone told me once to give away my Legos, and it used to be one point I didn't like giving away all my best ideas, but like let's brainstorm together, guys, right? Like,
yeah.
What I think, one of the ways that I would be convinced that quantum computers are on a path to doing dynamics, interestingly, is just see how much entanglement entropy you've generated over time. And I think this is, an easier way to think about the random circuit sampling, rather than saying random circuit sampling, okay, maybe it's hard to sample from, maybe it's not, but just thinking about how much entanglement you can generate. I think there's a number of tricks about how to get around the random circuit sampling, and one of the ones that I really liked was out of Misha Lukin and some of the guys over at Harvard and I think MIT. And what they had was just a way of breaking up the problem into smaller sections. And then you stitch it together, and you could do it on one processor. It was like a real cheap hack. It was
so like circuit cutting and circuit knitting. Is that what you're referring to?
I mean, something to do with the statistical nature of the benchmark that they're using, and because they don't sample the tails, you could cheat it. So basically, some way of hacking the statistic, and they could beat the random circuit sampling.
Oh, I see. You're saying classically beat the random circuit sampling.
Yes, classically, one processor.
Right. Well, and in fact, I believe Dori Darinov is on that paper.
We just
recorded our conversation with her a couple of weeks ago, so that's coming out shortly. Yeah.
There's a whole bunch of papers about this, but I think a lot of them, some of them are statistical hacking. They're just ways of kind of attacking the way that you've measured your statistics. But I think entanglement entropy or something of that nature to actually say how correlated are you across the whole number of qubits that you have. So if you can correlate so many qubits, evolve them in time, and there will be some point at which I say my time dynamics from a classical computer can't do that length of time. And I think that would be maybe not an easier way. I haven't crossed all the T's out of the I's, but some clever graduate student is waiting.
Some researchers have looked at like how large a GHZ state they've been able to produce. I think on one of the IBM systems they were. So that doesn't meet the bar. For you.
GHZ has very low. So when you write down the tension network, it has very low bond dimension. So
okay, it's too sparse.
Yeah, it's just not hard to simulate with the tension network.
Oh yeah, yes, it's a fun conversation at a high level, and again for our audience that may not be as committed fans of studying the mathematics, I mean, could we just like unwind a little bit? So this entanglement entropy and its growth over time, I think this is a wise remark. Could you sort of dig into that a little bit more? Just for our audience and give a sense about what is entanglement entropy and what does that mean for computation? That's because it's I think a cool topic.
So entanglement entropy, I guess, to kind of zoom away from quantum information science, and I think maybe to say what entanglement it is, just at some very easy level. My way of thinking about probability, my way of thinking about quantum mechanics, and my entry point to understanding all of quantum mechanics has really been through mathematics. And so when I think of how to describe quantum mechanics to somebody who's never heard of it, I always start with probability first. And so this is something I'm writing papers about probability first. I'm trying to figure out the best way to kind of teach someone who knows nothing about quantum, what is quantum mechanics? But if you start with probability, think of a probability vector and how probability vector can transform. You end up with Markov chains and some restrictions as to what can happen, et cetera, et cetera. And you can do the same thing for quantum mechanics if you treat the states in the right form. You start asking about how these states evolve and how they change, and this will then give you back all the formulas that you have from quantum theory quite nicely. So this is kind of how I think about what quantum theory comes down to. And so entanglement is just stronger than classical correlation. So if we think in terms of probability, if I have athletes playing a sport, you can imagine that athletes that play basketball might also be good at playing handball, because they're used to moving their hands around, and someone who does wrestling might also be good at doing jiu-jitsu. And so you have these kind of correlations because they'll be good at one sport more so than someone who's switching completely from basketball to a combat sport where they've never really had to contact somebody touch to touch, right? And the flip side, somebody who plays judo doesn't practice catching balls or whatever, moving their hand-eye coordination. And so these things are correlated variables, right? And this is correlation however you want to think about it. And there's different measures of correlation, mutual information between two variables. The entropy can be used to think about, how much missing information is there. And so all these terms are from information theory and thinking about correlations and different ways of technicality. And so we go to quantum variables. You have the quantum state, and I mentioned this whole idea of starting with probability first. The concepts don't change. You still think about two quantum subsystems that are correlated. You have the electron. The electron has a spin, maybe has a location in space, and these two variables might be correlated. Then these two degrees of freedom are entangled if those correlations go beyond what is classical correlations. But these are just another way of saying correlations. And there's no real distinction between correlations in the quantum and the classical case other than The quantum ones can reach higher measures. This is Bell's inequality.
Or is it also? You're right. Is it also saying there can be correlations in quantum systems that can't exist classically?
You have to be very careful. There's a bunch of technical statements that are all like
Okay.
applicable here, but like the idea is, yeah, that's exactly right. I mean, more or less, if we don't get into technicalities.
Okay.
I mean, these guys do
Okay.
quantum philosophy. They really think about what are the implications of, Bell's inequality being violated by this
Yeah.
amount, by that amount, beyond Bell's inequality, these non-local boxes, and there's a whole lot of theory behind this stuff. Yeah, but yeah, it's all related to correlations.
Yes, and again, just for the sake of our audience, it just feels like the soul of the claim for many people in terms of their justification for believing in the merit, the extra power of quantum computing, is largely founded on the capacity of these systems to witness entanglement and have a richer notion of state, which is harder to express classically. So, I mean, do I have that right? Am I on target on that? That's
I think
remark.
you're 100% right. I think that's at the heart of what is quantum computing. It's, I would say, more fundamental than entanglement. I would say coherence.
Yes.
Coherence is really what's allowing these correlations to be much stronger. And that's really how you can build these entanglement that grows in time, because you have all these coherences that are allowing things to interact differently than if they were incoherent. And if they're incoherent, then you're just back to ordinary probability theory.
Yes.
So what are the correlations you could generate with the Markov chain? Okay. And then you start thinking, if I have coherences, what are the correlations I can build beyond what I have with the Markov chain? And this is how you can think about how the quantum extension of probability starts to give you more power. And so those coherences, whether that ends up being useful in entanglement or useful in some other notion, sensing, for instance, loss of coherences might be another way to characterize the environment. So a lot of things you can use the coherences for that I think are more fundamental than just entanglement.
And then circling back to Kevin's original question, so how does that relate to increasing entropy, entanglement?
Yeah,
entropy?
so entanglement entropy is just a buzzword for correlations.
Okay.
That was a long story short.
And would you say coherence is, like, the simplest way to understand that is the period of time that a qubit is controlled, is able to be managed before its state falls apart, becomes noise?
No, I wouldn't characterize it that way. I mean, that's decoherence.
No.
That's decoherence time.
No, I'm saying, but the coherence is the time before it becomes decoherent, when it's under control.
I wouldn't put it that way. Not to say that I disagree with that definition. I think it's a reasonable definition.
That's fine.
But I think the way that I was meaning coherence was not so much in terms of how long you are coherent, but rather what you have when you are coherent. And so when you are coherent,
Okay.
of any sort, even slightly coherent, or whether if you're completely decoherent, then you have just a probability distribution. It's exactly a probability distribution. There's
Right.
nothing at all. Then you start. So if you think about the probability distribution as a vector, okay, imagine a vector inside your imaginary, podcast world. Yeah, exactly.
Podcast space.
Now turn
Yeah.
that vector on a diagonal of a square, and then all the off diagonal parts that aren't that vector are zero at the beginning. And if they're non-zero, then they're coherences. Those are all the off-diagonal elements of that matrix.
Mm.
And so all those off-diagonal elements, if they all disappear, then you're completely decohered. And if they start to populate, then you have some coherence. If you have a little bit of coherence, you can simulate this classically. It's not that interesting. If you have a lot of coherence, then it starts to allow you to correlate variables in different ways, to detect things about your environment, to do I don't know, super dense coding, whatever you want to do. Now you're using these off diagonal elements that give you more ability to correlate random variables than if you just had a vector. Now you have a matrix to think about everything, the density matrix.
Right.
Yes. And so this entanglement entropy is a measure, right, of the extent, the propagation of this entanglement coherence. And what you're sort of saying, I gather, then, is that you're measuring, the rate of growth of entanglement entropy over time is at least one way to capture the richness of the quantum state beneath. Do I have that correct?
Yeah, I think it's a pretty close to right. I think your summary is pretty spot on about thinking about how the time evolution causes correlations to build up. Are those correlations more than you could build up classically? I think is maybe a simpler way of saying it without using entanglement at all, right? It's just, it's like, just keep it simple, like you said, for everyone.
I think entanglements is still hiding in the word
It
correlations.
is, but like, if you don't know what entanglement means, don't use it. We'll just say correlations, the same thing, right? I mean, who knows what correlations are anyways, right?
And so I wonder, are there any specific algorithms or facets of quantum computing where this idea about measuring the rate of growth of entanglement entropy gives you insight or around the specific nature of the algorithms or their merit for quantum computation? I mean, help us frame that specific mode of analysis in some way that would help us see the landscape with more clarity.
I guess in many ways, the random circuit sampling problem was designed to do something akin to this. And I guess, Sergio Boixo and these guys thought about it for a long time about what to do. They still got defeated by one processor,
Man, it's rough. It's rough out there. Yeah.
But, if you think about what it's hard for a classical computer to do, if you think about something like tensor networks, so you can measure when tensor networks are having trouble to capture the state by what the bond dimension is. This is a way of saying correlations again. So technical way of measuring the correlations. And so you can just ask when your quantum computer has generated enough correlations, you can't simulate it any longer. Tensor network.
And in practical terms, this is really interesting. So I had two questions occur to me. One, I feel like I'm repeating myself. Maybe I'm having a hard time grabbing this. But when you talk about like the numbers of correlations, would that roughly in chemistry, going back to that the application in chemistry, would that sort of be analogous to sort of how whatever complex the chemical reaction, the chemical system is that you're trying to simulate?
Yeah, it's really a mess really when you go from quantum information science to quantum chemistry. Like the communities are so different, not different, but it's very smart people on both sides of the fence. In quantum chemistry, everything's antisymmetric because of this fermion thing. And there's a huge controversy about whether them being antisymmetric causes them to be correlated already. And because in many ways you could say, no, that's not enough to be correlated. It doesn't really count for anything. But then you have a very different notion of what a product state is if you allow it to be antisymmetric or if you don't. And so this ends up being a whole sub-literature about entanglement inside of fermionic systems that does not line up with any literature inside of quantum chemistry. So it's like
I see.
Two different ways to think about correlation have almost like very little overlap.
Do you feel like torn between these two worlds? Because it feels like there's very different sort of intellectual framing at this point in time in those two arenas.
So, at the risk of giving away my secret to getting
I'm readying my application.
The whole way that I've been able to manage, like at Dartmouth. So I started AWS about 2 years ago, but before that, I was managing a team, and it's me and some undergraduates that show up occasionally, and they come through. I had some really good undergraduates, but some of the best undergraduates came to my group, did fantastic things. We learned together, and didn't finish anything, and they just left. They're like, I don't feel like doing this. Okay, bye, and that's it. And then the graduate students come, they spend 5 years. By the time they're trained and excellent, they're ready to solve a problem. It's time for them to go. It's like, oh man. So it's like, I can't compete with like a full team full of PhD students, full of, the top, talent or whatever, to hire the best postdoc. If I get a good postdoc, they go work for these guys the next year. My best graduate students leave, go work for these guys. So I had to pick a topic that was interesting, that no one's really working on. That's really my way of kind of playing the game. And so the way I looked at it is there's a large overlap inside of what's happening inside of quantum information science, what's happening inside of condensed matter science, and what's happening inside of quantum chemistry that don't line up at all. And not that they don't line up in a bad way, but there's a lot of mismatch, even in terms of motivation. So I think people so one of my first articles I wrote coming out of grad school was computational complexity in quantum chemistry. This paper was computational complexity in electronic structure. This was with Peter Love and Alanis Guzik, and this was actually started off as a term paper for Scott Aronson's class.
Oh, cool. Name drop munch. You got Guzik and Peter Love and Aronson all in one.
Big names, man. Yeah.
Scott was on my committee, so was Alon.
Nice,
So,
nice, man.
It's
good researchers, all of them.
Yeah. So Scott had wrote a paper about why quantum chemistry is hard, and it was a comment on this paper about DFT and QMA hardness. This Quantum Merlin author, MP Hard. Doesn't matter if you don't know the buzzwords. But this is the optimization problem. So it's saying that this optimization problem in quantum chemistry is very difficult, and it's as difficult as other difficult problems that we know of. And that was what the crux of the paper was. And Scott had written the news and views for Nature, and I was so excited to read this. It's someone in the chemistry department. I was curious, like, oh man, there's some proof that why quantum computers can be useful in quantum chemistry. So I went down the whole rabbit hole. I sat in the class and tried to follow as much as I could of what Scott was teaching me about computer science. And then at the end, I wrote this paper about how this implicates electronic structure. And this paper was very hard to get published. Very hard to get published. It was very hard to get past referees. At the chemistry journal, they're like, this is not chemistry. You shouldn't send it here. This should be like this. You didn't explain this, whatever. But for me, it was also a place that no one's working.
Right.
It's a place that has a lot of intellectual degrees of freedom, a lot of places to work with people, a lot of places to learn from people, a lot of places to do new work that no one else is thinking about. And tensor networks, almost all the tensor networks on lattices. There's fantastic work by these guys thinking about Lieb-Robinson bounds and tensor networks inside of, 2D and one-dimensional systems. But what happens when you don't have any dimensionality? So in quantum chemistry, you pick these basis sets that are the s orbital and the p orbital, the d orbital, if you've ever seen like these blobs or whatever. But these things are huge relative to the size of the system. So the s orbital, the 3s orbital, the 2s orbital of the carbon is going to be as large as the full hydrocarbon, usually. The hydrogen orbital will also be the same size. And so there's no notion of lattice here. And so this really changes how you look at what physics you're learning, how these algorithms are applied, which algorithms work, which algorithms don't. And so we've been thinking a lot about basis sets in my group, but this is really one of the places that really causes a mismatch between quantum chemistry and condensed matter and quantum information science. And they think quantum information science will allow us to bridge that in a very interesting way. And that's really what I have my group working on, what we're trying to do before everyone realizes how cool this idea
is. well, the cover's blown to at least a few hundred people will hear this.
Yeah, give away my toys, right?
he's got a little bit of a decent moat that protects him, though, right? These cross-disciplinary subjects, and they're fascinating. There's so much high potential, but there's two completely different vocabularies of discussion, two completely different ways of thinking. So being able to commute back and forth between the two, that's a hard skill to do.
Yeah. So, James, do you think that kind of just begs the question? Do you think eventually these all converge? Does quantum information science end up bridging? Oh, well, that was easy.
Someday.
I mean, in many ways, even before quantum information science, quantum information science gives a lingua franca.
Yeah.
It's kind of like Python or something or like English, a lot of science. And I think quantum information science gives that language to bridge the two in ways that are going to be productive and at least well-grounded in some concepts. Whereas in condensed matter, you start off thinking about, you mentioned Hartree-Fock. Well, Hartree-Fock is also the basis for condensed matter and for DFT and for quantum chemistry. And all these things end up starting from the same place in terms of what they're doing. And then it diverges very, very differently depending on which applications are. And so zapping away from the applications, thinking about, the underlying infrastructure mathematically, conceptually, how do these things align is where quantum information science gives a nice way to kind of talk about these two different areas in a nice way. If I can plug one thing here while we're here,
please.
Giving away ideas. One idea.
As many as you want.
Yeah, well, great. So one of the projects that we're working on, and hopefully by the time this podcast comes out, we'll have a little bit more motion on it. But one of the things I'm really excited. So I'm on sabbatical this year, and I've been working on a few sabbatical projects in my spare time. But one of the projects that we're doing is to think about how do we use quantum computers to benchmark what people are doing today. And so we're thinking about the quantum computing, quantum chemistry benchmark, where we really have the same problems you have for density functional theory. And then the question is, can you reproduce these results? Or if you can't, how bad are your results now? and how bad are your results next year, how bad are your results the year after.
Mm.
But can you do standard basic quantum chemistry that's been going on for 50 years, 60 years at all, and get back a number that's meaningful? And how do you actually judge this? How do you set this up? How do you have this as a contest? This is really what we're working on now, to invite people to really think about this with us, that it's not just saying, here's the right answer, but here's how do we do it together as a community to focus people.
Is the challenge expressing that in code? And you mentioned Python. Is it writing the Python to actually run that on a quantum computer or a quantum simulator, or is that trivial? Is it implementation that's hard?
So I think for me, the motivation for the whole contest idea, I guess hopefully no one's mad. I'm giving away all my language. Like, if someone scoops me before I do this, it's fine.
Get a website up, James. Just get a website. Yeah,
we have one. We have one. Yeah.
Okay, well,
I'll give you the link.
We'll put it in the show. Yeah, it'll be in the show notes for sure.
Exactly. This will give us motivation to finish the webpage. So,
yes.
But yeah, the idea there is that you want to test out the devices, but the implementation is not necessarily the hard part. The hard part is that there's 150 papers in VQE.
Sure.
Mm-hmm.
Or 300 papers in VQE, or 50 papers. Shoot, 3 papers in VQE. I mean, I don't want to implement this for you. And so if you did an idea, and also I think even not just implementing it, but you have VQE as an idea, just to think about how much it costs to run a variational eigensolver. How much did it cost? How quickly did you converge? How good was your answer? What was your time to convergence? Was it cheap way of getting the right answer? Did you have to use quantum at all? Did you just use a quantum qubit to flip a coin and pick out 2 different DFT functionals? So there's a lot of questions that kind of come up pretty naturally as far as metrics go. But I think just having that question sharply defined and having some of the best minds come and think about it with us is really what we want to do.
Do you sort of think of this in terms of almost like a quantum chemistry version of CASP, of the protein folding competition that Davis puts on every couple of years?
Yeah, I think that's pretty similar. I think I think that's a similar idea. I would say a lot of the hackathons and Kaggle and things like this are similar. I think a lot of the quantum hackathons happen. I think my goal here is to have it more professional.
Well, and also having, I like the idea of having, it's a challenge, right? It's like a repeated, having people repeat, attempts at coming up with a better answer for a challenge. That's can be especially in sciences, it can be particularly powerfully motivating.
So, James, is this a bit like there's in the machine learning community, there's this thing called the I think it's the GLUE leadership board or something. It's a bunch of different competitions on natural language processing tasks, and they have then the best known implementation for cracking a particular NLP task, and then you just sort of like show who's up on the leaderboard and who's leading and how they're progressing. Is that the kind of concept you had in mind?
That's the concept we have in mind. Exactly. I think
powerful.
The issue
really.
about having it's hugely powerful. I think the hard part is if you think there's another really nice one that I think is a good analogy is the robotics challenge.
Oh yeah, no doubt. Right. It's just to show the current state of the art, and it keeps raising everybody's game because they can see what happened last year. Yeah.
Right.
Exactly. And so that's really, I think that's along the lines of what we're hoping for, is that it shows up like that you have such a hard technical problem that, if you, you come and try it if you're in high school, but you're going to really need to know some quantum chemistry, you're going to need some quantum computing.
Yeah, some no mess around
think
stuff,
about how the gates are designed. Yeah. I mean, I'm not knocking it. If you know what you're doing,
go nuts. But not
exactly.
for the faint of heart. Yeah.
Do you have a name for this yet, James?
Yeah, it's the Quantum Computing Quantum Chemistry Benchmark 2023.
Cool.
Love it.
Nice.
Wow, that sounds fun. Nice. Breaking news here. Thank you, James. That's cool.
Yeah, that's awesome.
Yeah, it is for a lot of people. We haven't invited anybody yet. So.
Well,
by the time this comes out, hopefully
at some point, yes,
gone out. But at some point, yes.
All right. Nice. Good luck on that, man.
Well, you mentioned what I know is another one of your favorite topics, which is how to teach quantum information, and your starting point being probabilities. That makes sense to me, but I know you've thought quite a bit more deeply than that. Are you saying at every level, is there an optimum sort of starting point in terms of age level, or I don't know? I'm just curious of your sort of thinking around education, because I know you think about it a lot.
I think a lot about it. Yeah, also with you.
Yeah, I know. That's how I know. I'm cheating.
So I would say the part that I guess we're on a podcast, so I guess I'll tell you about the stuff I don't normally talk to you about. So I guess we talk a lot about Q12 and these different K through 12 efforts and K through 14 efforts. I think what I've been doing with one of my other sabbatical projects is thinking about how to teach graduate level quantum information science.
Mm.
So my colleague Lorenzo Viola had been teaching this course, I think one of the earliest quantum information science graduate courses in the Ivies, and she gave it to me a couple years ago, and I have notes for decades, and this last time I taught it last year in the spring, I tried to write notes for every lecture. And so I did my best to write these lecture notes, but I'm okay as a writer, but I'm not that fast. So I wrote my notes. They were decent, proofread them once, gave them to the students. Okay. And they were like, these are really, really good. You should have given this before class so we could read these and then
Nice.
understand and then discuss them. So I was like, oh, you guys like the notes that much? Fine, I'll write them up. And so I've been working on this as a project to kind of think about exactly what your question was. How do you teach this the right way? Or at least my thoughts about it. And what I find really interesting is that I should finish this also quickly because I've been paying attention to how a lot of the modern work is coming out now. Post Nilsson and Chuang. If you look at John Waltrus is giving a really nice set of lectures, and the way he started off his lecture series is also with probability first. And he didn't call it that, but like he starts off with what measurement is of a coin flip or whatever. I don't remember exactly how he started, but when you start with what is measurement in probability theory, what do you feel? Are you Bayesian or frequentist? Whatever you want to feel about it, we have a discussion about this. But then we're done with philosophy after we finish that.
Right.
And this is my way of getting rid of that whole discussion, and not in a dismissive way either. That's saying that that's good research, fine, but that's not what quantum mechanics is. Quantum mechanics is what you do after you decided those questions.
Yeah. Shut up and measure, or calculate. Shut up and calculate.
Yeah, I mean, however you want to look at it, but like you could say the same thing about probability, right? You don't have to think about the philosophy of probability. You want to calculate what the outcome statistic is. For the T2 test, it's some numbers you put in, ANOVA, and it comes back out, right? It's it's not really a real question of what does this mean. It's just a bunch of numbers.
Right. And is the goal to put together? Are you going to share that online, or are you going to write a book, or both? What's your thinking?
Isn't that the same thing?
Yeah, I guess so.
Yeah, I mean, I what I want to probably do is complete the notes at some point that I'm happy with them, give them to people to use in their classes, and see if their students are happy with them. Take some feedback, round it up. But the first few chapters are pretty much what I think it should be, and what I started off the book with was kinematics of probability. That you do probability theory where you just hold three axioms that the numbers in the vector need to add up to 1, they need to be greater than 0, and they should all be positive.
Yeah.
And but when do you bring in negative probability, since that's such a...
So my approach to it has no negative probabilities. Okay, this is okay. There's Wigner distributions, but I think it would be a really interesting project for someone to go back and see what I did in terms of Wigner distributions. But I have no idea. I did in terms of kinematics of the vector, and so this vector has these properties you have to maintain, and you can go through probability theory, get out Markov transition matrices, the population, dynamical version of it, where you basically have what happens is differential equation. You can get out, normalization, you get out sharp distributions, all sorts of things about measurement. All these things happen. That entire kinematic framework, you then boost over to quantum. You follow the same exact steps. Okay. And you start off with the density matrix, and I always use the term probability density matrix.
Yes.
Because then it makes more sense, because the probability density as a matrix.
Yeah.
So it's probability density matrix, and then you just look at the kinematics of the probability the kinematics of the probability density matrix, and that gives you back quantum channels, the Lindblad equation, the Schrodinger equation, unitary versus non-unitary evolution, noise. All these things show up immediately and with no context of quantum, just kinematically. These are the equations that dictate how this has to stay a vector that has eigenvalues that are all positive, eigenvalues that are greater than 0 or greater than or equal to 0, and eigenvalues that are sum up to 1.
Yeah.
And that they're real. That's the
real.
So that the real is that it has to be Hermitian.
Yeah.
that they sum up to one is the trace is one, and then all these things did allow for coherences, all these
Yeah.
dynamics. You get back the full structure of quantum mechanics without doing any further physics.
Yes. Yes.
Wow.
Really interesting. It's
That's
so
cool.
great to hear somebody focusing on the pedagogical concerns. I mean, these are aggressively non-intuitive concepts, some of them, right? And there's so many students that want to.
Probabilities.
Yeah, exactly. Yeah.
Yeah.
Yeah, and eigenvalues, all that linear algebra, and all that complex analysis. There's a lot of stuff under the hood there. So it's good to hear somebody really focusing with rigor on decent pedagogy, because it's no walk in the park.
I also say it's really interesting, like for quantum mechanics, right? When you go to atomic physics, the first thing you encounter is angular momentum. Angular momentum is so hard to understand without quantum mechanics. And it's like, you really have to go to a merry-go-round, think about when you throw the ball, which way is it going to go? And like all sorts of like, very basic questions about what angular momentum is that, are very tricky to do even without quantum mechanics. And so when you go to quantum mechanics, it doesn't make it easier to understand a complicated subject. And the same thing's true of correlation. Causation versus correlation. Should I use this test or that test, or how do I just statistically significant? All these different questions. Statistics show up almost immediately when you go to quantum mechanics, because it's just an extension of probability. So you didn't get past probability by going to quantum mechanics, but rather it's underlying it.
Yes.
And so if you didn't understand it then, you're not going to understand it by hopping to quantum immediately.
That's an interesting, quantum and AI often get grouped into the same category in terms of technology. And I often sort of wondered about that. But what you're saying kind of suggests, if you think of AI and ML, current iterations of AI and ML as being rooted in data science, what you're saying is sort of that, that's probability and statistics that underpins all the machine learning models is the same basic tools you're using in quantum information.
Yeah, in many ways, yes. So they're extended from the tools that you're using, machine learning or any other statistical analysis. You can extend them to quantum, and that's what a lot of the papers are, just extending classical concepts to quantum, and then you get whatever you were doing in probability theory, you can then do it in quantum theory.
You mathematicians, so clever. I do think, it's so interesting, James, that you've got this sort of journey from, a deep interest in math, and then almost like pre-med, and then a turn into chemistry and physics, and then quantum chemistry, and then physics. You really do exhibit sort of different modes of thinking, whether you're conscious of it or not. I hear more physics, more chemistry, more math kind of coming out in different aspects of how you talk about this stuff. It's fascinating to me because I'm not any of those three things. But my conceptual understanding often leans on one or the other sort of frame of reference, and it's just really interesting to hear you flipping back and forth between them in a way that's pretty unique, I think.
Yeah, I can point to my research group. I think one of the things that I really had a lot of fun is that at Dartmouth, a lot of people come, and they come for whatever reason. They didn't end up at Stanford or Caltech or whatever. They're at Dartmouth, so it's like, all right, come on down, guys. We're going to make you the best scientist you can be. And I've had some really good scientists who are about to leave my group. Some really good scientists in my group, but because they're all in my group, they all getting indoctrinated in this like mix of chemistry and mathematics and quantum information science, and this kind of explore this area that no one's in. Just have fun and just kind of go look around and see, what do you find interesting about fermions today. And like, it's we're in Hanover, New Hampshire. It's like, relax, we're not going to compete with Boston, or we can't go against the the entire algorithms team at Amazon, right? We're going to kick back and do our little niche and have some fun and talk about it. So
yeah, nice gig.
That's really cool. Yeah.
And so we have a real good mix of talents inside my group. So it's a lot of people who, some of them focused on math, some of them are trained to be quantum chemists, some of them are, one of my graduate students is really, really good at quantum chemistry. He's about ready to go to become a coder or a quantum chemist. And so we got alumni headed off to, one of them will join us at AWS.
Oh, fantastic.
Different team.
Oh, cool.
Nonetheless. Yeah.
Very cool. Well, do you think, and I'm mindful over time, so here's your wrap-up question. Do you think, you mentioned, quantum information theory or science is sort of lending a lingua franca was the term you used. Do you think that eventually this does, software eats all of these disciplines of science as well, and we end up, being, we end up with scientists being coded, they're writing code, and that code happens to be solving problems in chemistry or solving physics problems or solving, other scientific problems through writing software?
That's a nice question. I like that question. I think not. And I'll give my argument for it. I think this question touches really nicely on this whole zeitgeist of AI and people worried about are they going to take our jobs? They're going to do this, that, and the third. My thing is that there will always be smart humans, and I don't mean that as up or down, whatever. It's just if you have a bell curve, there's going to be somebody at the far end, somebody of it, right? There's kids that are at the far end of that will always figure out how to use the tools and how to make better versions of the tools, and they'll figure out how to play with these things in ways that we haven't thought of. And I think that's really where you get creativity. You get whether or not you want to use a computer. A lot of scientists don't use computers, and they're still fantastic scientists, take entire journeys inside their head, building mathematical structures, and they don't bother to code it up, and then they give it to someone else who codes it up. And I think there's a lot of space for people who are intelligent to just get together and think of more intelligent things. And the tools that are coming out now will only help them do more. And they'll be able to get back to the tool. And whether they don't write any code at all, they tell ChatGPT to write it up. Here's my great idea. Code this thing up, and then they can do 10 ideas in a day rather than having to spend all day to learn C++ and learn Python. They can just say, hey, here's my code, man. I want you to code up this differential equation for me. And then
that's awesome.
They can learn something else. And they could just
right.
A great perspective. It's an amazing time to be alive in many ways, huh? Yeah, we're lucky.
It is.
Yeah.
It is.
I like spell check. I can't believe what these things can do.
Dude, I'm with you, man. Yeah, super useful.
And glasses. Glasses are cool too.
Cliff notes, that was also fantastic, man. These things are doing automated.
That's great, James. Any last thing you want to plug, or any last thing words you want to leave us with?
I didn't think about this.
No pressure.
No
pressure.
It's all here. It's all here already. Yeah, I don't know. I wish I had better than I don't know.
No, we got some great material.
We had one great ending. I just wanted to give you one last chance because I kind of asked the last question.
It feels like
you knocked it out of the park.
When you're at the interview and they're like, you should have a question to ask.
No. Okay, another fantastic conversation we had there, Kevin. I really, really liked James's views on where he thinks quantum computing will first sort of provide practical advantage in quantum chemistry. It's not sort of the standard view that he adheres to, right?
Quite so. I mean, look, this whole distinction, right, between finding a ground state of these systems versus looking at the time evolution of them is a distinction that is not, I think, commonly talked about. And it really, I think, elucidates whole new domains where perhaps quantum computation could make gigantic inroads and perhaps even pioneer very novel new forms of science and applications in the real world. So powerful insights, I thought.
Yeah, and his reasoning really resonated with me because, as he pointed out, classical computational chemistry has really been focused on ground state estimation, ground state optimization for quite some time, and there's really sophisticated.
Now, yeah.
Right, that's a fairly long time, and so there's really powerful tools to get good results in that way, and so it's unlikely that these super early stage quantum computers are going to outperform the best sort of classical approaches that we know today, right?
Yeah, but there could be all sorts of novel problems out there that have just never been investigated before because they're so challenging. That could be so. It's resolving, I think, with better clarity, optimism in a particular area, grounded optimism, and then skepticism about other areas where it's not really. I think there are a lot of room for progress. So
you're right. I mean, it's difficult, as James pointed out. It's difficult for people to bring to bear sort of their scientific inquiry in that way with quantum computers, because that's not their sort of starting point. I think it speaks to James's sort of novel collection of different disciplines and different sort of frameworks for understanding, that he's taking this sort of blank sheet of paper kind of approach to what are these machines potentially good for. And I'm hoping, I mean, it was great to hear about his quantum benchmarking event that he's planning this summer. Hopefully
that sounds cool,
help.
Actually.
It really does. Yeah, it really does. So we'll definitely have a link to his site in the show notes when this gets posted, and we'll keep you up to date. Maybe we can do some kind of special episode on the outcome of the first quantum benchmarking
cool. No doubt.
event. Yeah, that'd be great. All right.
Awesome.
Well, thanks, Kevin. See you next time.
Amen. See you then.
Okay, that's it for this episode of The New Quantum Era, a podcast by Sebastian Hassinger and Kevin Roney. Our cool theme music was composed and played by Omar Costa Hamido. Production work is done by our wonderful team over at Podfi. If you are at all like us and enjoy this rich, deep, and interesting topic, please subscribe to our podcast on whichever platform you may stream from. And even consider, if you like what you've heard today, reviewing us on iTunes and or mentioning us on your preferred social media platforms. We're just trying to get the word out on this fascinating topic and would really appreciate your help spreading the word and building community. Thank you so much for your time.